This is the second part of the Week 6 lecture for 2P21. Jeff Boggs here. For this section of the lecture, we are going to talk about different forms of quantitative analysis, sort of basic or entry level, if you will, if you want to think of them in those terms. And in particular, because things go better with examples, I will be referring to the railroad scenario handout that you should be able to find on the Sakai page. In this scenario, in this handout, you've been hired to answer the following research question. Are property values lower the closer a house is to the railroad tracks, or in this case, a railroad track? And so in this scenario, you've been hired by homeowners to determine if proximity to a railroad lowers their property values. The railroad claims that property values are largely determined by the age and size of the house, and that occasional noise from the railroad has no or at most minimal impact on property values. The town council meeting is tomorrow. Homeowners, as you might imagine, are arguing that being close to the railroad is harming their property values, and they want the city to do something about it. What I want you to do at this point is to pause the video and examine the handout now. Before we go any further, take a couple of minutes to look it over and then come back to the next slide after this. In this example, you have collected some preliminary data. And while the number of observations is smaller than you would like, optimally, you would have data on every house in the community, but you don't have that. Instead, what you do have is a random sample that contains 33 observations from within about 600 meters of the railroad. And this data that you've collected, and we're not going to go in right now into which kind of random sampling procedure you used. We'll save that for later. You have collected data from 33 houses, and you did it using a random sampling procedure, which means that you can make generalizations about the larger population of homes that this is drawn from. And so these are 33 homes that are within about 600 meters of the railroad. And we're assuming that, at least in this particular town, that no one who lives any further than 600 meters from the railroad has complained about its sound. If we look at the data, we see that we have data on square feet. So this corresponds in North America to the amount of area on the ground floor of a house or of a building, or at least when you're looking for houses, tends to be the ground floor of the house. So it doesn't include the basement, it doesn't include the second or other floors. We also have data on the year that the house was built. So this lets us understand how old a house is. We have data that we're calling lot, which is actually the lot size in square feet. So the lot size is just basically how big is the plot of land that comes with the house. RR stands for railroad, and RR in this case is a binary variable. So it's basically a nominal level. Actually, this would be ordinal, I guess. But a value of 1 indicates that the house is within 100 meters of the railroad line, and a value of 0 indicates that the house is further than 100 meters from the railroad. So actually, we don't even want to call this ordinal. We just want to think of that as, well, I guess we can think of it as ordinal. Where's my pen? There it is. Okay. Even though we have it kind of ranked in a weird way, right? So for, nope. Let me come back here. Then we have RRDIJ, so that's the distance from the house to the railroad. We'll talk about that in a moment. So here, railroad. So within 100 meters equals 1, and if it's beyond 100 meters, then we give it a 0. So all the houses are either receive a 1 or a 0, depending on how far away they are from the railroad. And then RRDIJ, so DIJ is used in geography, or at least in transportation geography, to mean the distance between location I and location J. So RRDIJ is just the distance between a particular house and the railroad, in the railroad line. Value is just the most recent value of the house as it has been assessed by property assessors. So that's going to be, nope, let's get rid of that. So value is just going to be in dollars. And then the last one we have is age. So age is how old the house is. So when I originally created this data, or these data, I guess, it was 2018. So you take 2018 minus year, and I suppose we could say year I. So that I just corresponds to the actual house that we're talking about. And so 2018 minus whatever the year is. I think the oldest house that we have is 98 years old. So that is 1, 2, 3, 4. So that's the 5th house. It was built in 1920. So if we say 2018 minus 1920, that gives us, so 18 minus 10 gives us 8. So that becomes a 0, but then it becomes a 10. So, nope, hold on. 18. No, that should still be. Yeah, this is embarrassing. Okay, I know that it should be 98. So we know that should be 98. So I'm not going to take this as an opportunity to show you how much arithmetic or subtraction I've forgotten. So I know that 2020 minus 1920 is 100. 2018 is 2 years less. than 2020. So 100 minus 2 gives me 98. We'll kind of leave it at that and look the other way. All right. So there are the variables that we have. And so often in quantitative research, we end up coming up with variables. And so these are things that we think are important and worth measuring, right? So we might think that square footage is important for houses and their property values, right? And we could even say, so let's maybe go over here. So square footage in general, as square footage gets bigger, probably imagine that the house is worth more. For year, we don't really know, right? So it might be that older houses are ricketier and aren't built as well. That's actually probably not necessarily the case if they've survived this long. And so it might be worth less than newer houses, or it could be that older houses that are still in existence are worth more because they're rare or maybe they actually are built better. So we don't really know. So we'll put a question mark there. So we don't really know how this affects property value. And so here in this, I'm putting like impact on property value. And we'll put up here, we'll even say like theorized or suspected. So theorized impact on property value. So we think square footage, bigger houses are probably worth more, all other things being equal. For age, for year that the house was built, we're not really sure. For lot size, bigger lots, all other things being equal, are probably worth more or lead to the house costing more. Railroad. So for this one, if it's within 100 meters, it's probably, if the homeowners are correct and houses close to the railroads get a lot of noise and that makes them harder to sell or to live in, then we might actually expect for this one that if it's within 100 meters that it's going to be worth less than if it's more than 100 meters. But it's hard to do kind of pluses and negatives because this is really more of a nominal variable here. So for the distance, though, generally, if what the homeowners claim is true, if that, noise lowers your property value, and noise from the railroad lowers your property value, then the further away you are from the railroad, you would expect, so as this number here gets bigger, we would expect the house to be worth more money. And then for value, we're already asking questions about that. So, and for age, so again, we're not really sure because it's basically like year, except instead of giving us the year, so 1920, for instance, it actually, we have just calculated how old was the house in 2018. So these are examples of variables. And with variables, with numerical or with quantitative analysis, you often want to think about how they might relate to each other. And we've done a bit of that over here by theorizing the impact on property values. At this point, we want to ask, how can we analyze numeric data? And remember that to analyze something means to kind of break it down into its parts. Sometimes it also means to look for patterns or to interpret these patterns. And so, at least in this particular instance, let's kind of have more of a loose understanding of what analyze means. So in this case, the first thing that we could do with this quantitative data is describe its distribution using histograms or measures of central tendencies or measures of dispersion. All right, so a histogram, and let's talk about distribution first. So the distribution is basically tells us something about, how many of the values are high values, how many are low values, how many are close to the middle. And a histogram provides a picture, if you will, or an image to help you sort of understand the distribution of values in a particular variable. Measures of central tendency, you're already familiar with the mean, or I guess it's technically the arithmetic mean, but you probably call it an average. But there's a couple of other measures of central tendency like median and mode, and we'll look at those in a minute. And we can also find those on our histogram. And then there's something called measures of dispersion. So this tells us, how closely or loosely packed are all of the observations around whatever the middle is. And so one of the things that we can do with numeric data then is use it to just describe the distribution of these of each variable that we're looking at. And often that is the first thing you do in any kind of quantitative analysis, just to get a sense of, of your data. Another thing that you can do is you can compare this data set, or like you can compare groups inside this data set with other groups inside this data set, or with other data sets as well. And we'll do that later as well. And then the third thing that you can do is look for associations between variables. And so when I was on the previous page putting like a plus sign or a question mark next to a variable, there I was looking for, I was kind of theorizing an association. So in general, I would think that houses with more square feet, all other things being equal, will tend to sell for more than houses with less square footage. Likewise, houses with bigger lots tend to sell for more than houses with smaller lots, right? So those are some examples of associations. And with associations, there are both kind of numbers that we can use to describe these associations, but also we can use images to see these associations. Let's move on to first describing this distribution. So how can we analyze numeric data? So the first thing that we can do is we can just describe a distribution. So we can use histograms, measures of central tendency, or measures of dispersion to describe the properties of a particular distribution. Let's just go on to that, because a picture might actually help you more than me yammering on. Here we have a histogram. It is not a bar chart. A bar chart is something else. It looks kind of like a bar chart, but do not call it a bar chart. It is a histogram. And this is actually an absolute frequency histogram. And I used Minitab, a software package, to make this, using the data that you have on your data sheet. So this is a histogram of the age of houses that are in our sample. And the way it works is that we have bins. So fiddlesticks. So it shows us the shape of the distribution, but let me just write a bit more. And it shows us the shape of the distribution by lumping the data into bins. So B-I-N-S, bins, or categories sometimes people will call them that. And so this bin up here contains all of the houses that are between 10 and 19 years old. So we could put 10 to 19. And we see that there's 4 houses in that bin. So there are 4 houses in our sample that are between 10 and 20 years old. So here then we have 20 to 29 years old. So we have 2 houses that are between 20 and 29 years old. In this bin, we have 30 to 39. So we have 2 houses that are between 30 and 39 years old. 40 to 50 years old, we only have 1 house. So it's going to make that a little harder to write. So 40 to, nope, hold on. 40 to 49 years old. The next bin then includes, and so there was only 1 house between 40 and 49 years old. So this would have been in the late 1960s to the kind of late 1970s. And when you're making histograms, especially of age, so this age of the house, so this is basically when was the house built and what year was its construction completed. It's a way to think about that. When we have those, especially this kind of time data, we might think back to what was happening, at this particular time in history and maybe the national economy or even the international economy. So there would have been about between 40 and 49 years ago, we would have had 2 oil shocks. So the one in 73 and the other in 79, if I remember correctly. And those really drove up oil prices and also were associated with high rates of inflation. And so the economy, to put it colloquially, tanked in lots of countries. So that could explain why we have a low number of houses, a small number of houses, only 1 being built in that time, right? Then in this bin, we have houses that are 50 to 59 years old. And we have 4 of those. In this bin, we then have 60 to 69 years. This one up here has 7 houses that were built between 70 and 79 years ago. Here we have 6 houses built between 80 and 89. And then for this one, we have, what do we have? We have 4 houses built between 90 and 99 years ago. All right. So this is then a histogram. And it shows us literally the shape of the distribution. If we had, instead of using bins that were 10 years wide, if we had used bins that were 1 year wide or 5 years wide, the shape of our distribution would be somewhat different. So in those cases, there might actually be there might be gaps. So places where there were no houses built in a particular 5 or 1 year period. There is a fine art to making histograms in which you really want to try, to make your histograms neither too large nor too small. And that's not really what we're going to talk about here today, but just kind of bear that in mind. So, we could have also made a histogram that just had 2 bins. So one could have gone from basically, actually, wait, let's step back. We see that here in the 0 to 10, or the 0 to 9 years bin, that there's actually no houses. Nobody built a house in the last 10 years, right? So nobody built a house in the last 10 years. We could have also said, we want to go from 0 to 50, And so we could have had a bin there to there, which then would just add up all of these. And then we could have had another bin over here from basically 50 to 100, which would then, we have two bins, each are 50 years wide, if you will. And, the second, the older bin, the 50 to 100 bin, or I guess 50 to 99 technically, that bin would actually be much bigger than the first one. So when you're making bins, you don't want them to be either, you don't want too few, nor do you want too many. I'll leave it at that though. In addition to making a histogram, so that is the nifty diagram, or the nifty image that we saw in the previous slide, that is not a bar graph, mind you, because bar graphs don't show frequencies, or at least frequencies of a variable within the same population. We could also calculate things called measures of central tendency. So measures of central tendency, essentially, when you see the word central tendency, this is like a fancy way to say the middle. So, or middleness. Middleness, if you will. All right. And there are a couple of different measures of the middle. Yeah, so they describe the middle or the center of a distribution. And there are a lot of different measures, but usually if you learn any, you learn these three. So there's the mode, there's the median, and there's the mean. And so the mode is the one that occurs most frequently. Nope. Which we'll see here on this slide. So what is the mode? So the mode describes the most frequently occurring observation in a distribution. So as opposed to the bins that we saw in the histogram, this refers to, so remember those bins in the histogram were 10 years wide. So in this case, the mode would be, if we're looking for modes for the age of these houses, it would be what age occurs the most. And the thing about the mode is that it is the only measure of central tendency that can use nominal, ordinal, interval, or ratio level data. Because even if you're comparing cats, dogs, and ferrets, you can still say, there's 32 ferrets, 57 cats, and 2 dogs. So in that case, 57 cats describes the mode in terms of, pets, I suppose. The median, M-E-D-I-A-N, not the medium. A medium is a person who alleges to speak with spirits, or it is sometimes the singular for media. So we're not interested in those at this point in time. Instead, we are interested in the median. And so the median is the value found at the 50th percentile. And this might be a real value or it might be a synthetic value. We're not going to go too much into that. So, but basically it is, 50% of the distribution, 50% of the values are to the left of this value and 50% are to the right of this value. And the cool thing about the mode, the median, and the mean, which we'll see on the next slide, so the cool thing about all of these measures of central tendency is that we can actually also draw them on to a histogram after we draw the shape of the histogram. The median, unlike the mode, can only be drawn for fiddlesticks, for interval or ratio level data. So if it's nominal or ordinal, you're out of luck. And the way that we find the median is that we sort all values from smallest to largest and then figure out which of those is the middlemost value. So in the case of age of houses, we would first find all of the 33 ages, and then we would arrange them from youngest house to oldest house. And then because there's 33, it would be sort of a value in between, let me see, 17 times 2 is 34. So it would be kind of a value in a position that no number actually occupies. So, but, oh, actually, no. If it's an odd number, it depends. There's actually two ways to calculate the median, at least two. This drives me crazy when I have to teach this stuff, because invariably a textbook will use one or the other, but not mention both of them. But one way that you can identify the median is to, if it's an odd number, find the one that's actually the odd number right in the middle. If it's even, then it becomes a little more complicated. But I will stop there. So the big point here is that the median is at the 50th percentile. So half of the observations are to the left of it on our histogram, and half would be to the right. And the third common measure of central tendency is the mean. And this is, it just describes the average, like the average value. So in a school, when you learn to calculate averages, so if we had 33 houses, we would add up all of their ages and then divide that sum by 33, and that gives us some number. That is the mean. And technically, it's the arithmetic mean. Arithmetic. That might actually need to be an A, which there's also like a geometric mean. We're not going to go into that. All right. So we've got this mean. So that's another way to measure central tendency. And it also can only be calculated for interval and ratio level data. One of the cool things about the mean is that you can compare it to the median, and then that tells us, do we have a symmetrical distribution? So around its middle point, does it basically look like a mirror image on the right and on the left side? Or is it a bit lopsided? Or is it really lopsided? So you already know how to calculate an average, right? So we've got, in this case, 33 houses. You add up all of their ages and divide them by 33. And that gives us the mean age of the houses. Now let's look at that same histogram and figure out where do these measures of central tendency fall on this particular histogram. And you at home, with this sheet that you have in front of you, here it is flopping about in my room here. Actually, I'm in my kid's room, making sure fever doesn't spike. And so with this data on this sheet, you can actually calculate all of the things that I'm showing you. And if you're like me, you'll have used a computer program to do it. So in this case, I used a statistical software called Minitab, but Excel will do a lot of this stuff as well. So we first see that when we add up all of the ages and divide them by 33, that the mean is 62.7. So almost, so that the average age of houses in this sample is 63 years old. If this really is from a random sample, then this is we can think of this as a reasonable estimate of the actual age of the housing stock within. So housing stock is a fancy way to say houses. So we can think of this as a reasonable estimate of the age of the houses within 600 meters of the railroad track. So they're on average about 60, not quite 63 years old. The median value is 71. So let's look at that. So 71 is kind of over here. You can't really see that very well. Let's try this. Yeah. So that's supposed to be a straight line. It's not really working. So 71 is over here. So this means that basically from here to there, this is like half of all the houses, or observations, if you will. So half of all the houses, or half of all our observations, are 71 years old or older. Over here, then, this means that here's the other half of the houses, half of the houses. So half of the houses are under 71 years of age. So, I would say that's some fairly old housing stock, though it also then really depends upon your context. So if you're in some cities, this might be relatively new. So maybe in case of some cities in Europe that haven't grown a lot and also didn't get blown up during the Second World War, we might see a distribution like this as well. So this might also be the kind of distribution we see in an area that is now pretty well built up and suburbanized long ago. So, but that interpreting what we're looking at depends upon our knowledge of that particular subject area. So in this case, I'm drawing on my knowledge of urban and economic geography. So it might be that if this could be age of, I don't know, elephants. Elephants can live a long time. So in that case, if this were age of elephants, you might interpret this then, with your knowledge about particular elephant populations in, depends on whether they're Asiatic or African elephants. So in that case, then which kind of subspecies? Okay. What else can we do here? So we've done the median, the mean. We have not yet identified the mode. And so the mode isn't necessarily going to be all that easy to spot in a histogram. Sometimes it is, sometimes it's not. So if this was a histogram where each interval was 1 year, then we could spot the mode pretty easily. Okay, actually, some people would argue that if we're just looking at the binning, that basically this is our mode. So this 70 to 79 years, so I'll put mode. Oh my God, that looks terrible. Hold on. Fix this. Let's go back here. There. Okay. So if we think in terms of our bins, then we've got this. That's the mode of our bins. It's kind of right there. However, if we look at the year in, year out data, so we looked at the 33 observations, we'll actually see that the mode is 94. And that's because there are the 94 years appears 3 times in our data set. And you can look at that by looking at your sheet and then going through and just figuring out which value happens the most. There are other cool things like box and whisker diagrams. Those are totally cool. Or sometimes not so much a box plot. Box and whisker diagram can help you find this, but we don't have time to cover those. But I like them because they've got an excellent name. Let's think about what we're doing. We are talking about ways to describe numerical data. The first thing we talked about was a histogram. That helps us understand the shape of our data, or of values in our data set. So in this case, we had a histogram of age. We then talked about measures of central tendency. That helps us understand where the middle is, or the center within a distribution. And now we're going to talk about measures of dispersion. Measures of dispersion describe the spread of a distribution. And so, basically in the case of the years, are they all close to the middle of the distribution? Whether that's maybe the median or the mean, or are they more spread out? So you might think of dispersion as, compactness, or squishedness, not that that's a real word, or spread, right? And while there are a lot of ways there are many different measures of dispersion, the two that you'll come across most of the time are something called range. And range is just the difference between the highest value and the lowest value. Or sometimes it's described in terms of like what's the maximum value, what's the minimum value. So for this, we have like a maximum value. So what is the maximum age and what's the minimum age? And I believe the maximum age was 98. If I look at this, yeah, so 98. And the minimum age, if I look at the data sheet, is minimum age, I think it's 13. Yeah. Just check again. Yeah, 13. So we take the oldest house, and then we take the youngest house. We subtract the youngest from the oldest, and this gives us 85. So our range, the distance between our minimum and maximum age values is 85 years. There's another measure that's a little more complicated to calculate, and we'll rely on software to do that, is something called the IQR, or the interquartile range. So this is just the distance between oh, that doesn't look good. Looks like a 6. Is the distance between Q3, which is our third quartile. So with this, we divide our histogram into quarters so that each section, each bin, contains 25% or 1/4 of our observations. So 1/4 of our houses fall into each of these. And it gets a bit wonky when you have an odd number, but we're not going to worry about that too much. So we take the third quartile, or sometimes this is called the 75th percentile. So it's basically, you find the 50th percentile, which is the median, and then you just move up 25 percentage points from that to get the 75th percentile. And so we have the that, and then we we subtract the first quartile, so Q1. So that's the first quartile. And what this gives us is a range. It basically shows us, how many, well, what it shows us is if you go, so the first quartile is 25% less than the median, and the third quartile is 25% more than the median. So the interquartile range captures half of all the values. So it basically is one way to get it spread around the middle. We might call this the 50% around the middle, or technically the 50% around the median. Now, there's also actually something called the standard deviation, and that's calculated from the variance. We're not going to go into those right now because those are a little trickier, but in a stats course you would learn those as well, and those are other measures of dispersion, but we're going to stick with these right now. Recalling what we just talked about, we see here in this histogram, the same histogram we've seen in the earlier slides, this red line, or I suppose it's like a giant bracket, if you will. What I'm showing here is the minimum value was 13 years, so that the youngest house was 13 years old. The oldest house was 98 years old. So the distance between 13 and 98, remember we calculated this to come up with the range, was 85 years. So the range is 85 years. And one thing to recall then about histograms is that your bins don't necessarily have observations from each year, in this case, that are contained within it. So this one goes from 90 to 99. I guess technically up to 100, I guess. So, and at this point, the oldest house that we have is actually 98 years old. So we don't have any houses that are 99 years old. And if they were 100, if we had one that was 100 years old, it would technically then go in the bin that is over here where my mouse is moving. But we don't have any houses that old. So here we see the depth, I guess we see the range. So when I was yammering on about the range, this gives you a sense of it. So 85 years is the range. It's the difference between the oldest value and the youngest value, or the oldest house and the youngest house. We also can look at the, oh, hold on, I got some background noise here. Hold on. We can also look at the interquartile range, which is covered by this curly bracket that we see. So the first quartile sort of ends at 43. So that means that 25% of all the houses are 43 years or younger. So if we go here, so basically, oh, fiddlesticks. Draw, that's supposed to be a straight line, goes up to there. So this means that 25% of the houses, or 25% of our sample, are, less than 43 years old, which then means that 75% of our houses are more than 43 years old, or sorry, are 43 or more years old. So that's the first quartile. The second quartile is 85.5. So this means, if we, I don't know if you'll see this. So there. So what this means is that 25% of our houses are 85.5 years or older. What this area here in the middle, so between the first quartile and the third quartile, and which is centered, as you might suspect, on the median, which I can't remember what it was, 62.7 it might have been. Anyway, so that 62, whatever the median was, it's kind of like over here, so we'll say that's the median. This IQR, this interquartile range, that captures half or 50% of the houses. So 50% of the houses are somewhere between 43 and 85.5 years old, or probably 85.49999 years old. So that is a demonstration of how we can observe the interquartile range on a histogram. I think that's all for this bit. If we recall that we are talking about how do we analyze numerical data, we just talked about 3 different ways to describe your data. We can also, though, talk about comparing it. So you can compare it with maybe another data set, or look for differences within groups within your own data set. And in this railroad example, an easy way to do this is to look at differences in age of houses based on whether they're close or far away from a railroad. So we could ask the question, are older houses found within 100 meters of the railroad? And actually, for this, we might even want to say, are older houses more likely to be found? It might be a better way to phrase it, now that I think about it. Or we could say, do older houses tend to be found within 100 meters of the railroad? What we can do is, thanks to the joys of modern computer technology, that means that we don't have to slave away. Once we would enter this data on the sheet into a spreadsheet and then just import it into even Excel, but I actually used Minitab to do this, another statistical software package, we can say really quickly, just issue a command, our houses, we can issue a command that prints out these data. And so what we want to look at here, just to remind ourselves of what all this gobbledygook means, is here we've got railroads, right? And so a 0 in this case means that it's far away. So, and by far away, it means that it's 100 or more meters that a house is 100 or more meters away from the railroad, whereas a 1 means that it's close, or that it's within 100 meters of the railroad. And what we can do is take the, how do I want to do this? We could actually just find, remember the mean is just the average. We could find the average, or we could find the median. So remember, that's the 50th percentile. And we could compare to see if, is the mean, are they pretty close to each other, or are they, really different from each other? And if they are close to each other, now there are in inferential statistics a whole slew of ways to determine whether something's close or not. We're not going to go into that. But if we just look at this and just think in terms of like your garden variety mean or average, here we see that places that are further away are 61.6 years of age. So let's round that up to 62. And then places that are that are within 100 meters are pretty close to 66 years of age. So, on the surface, this suggests that places that are further away tend to be newer or younger than places closer to the railroad. And then if we look at the median, we see that the median age, so the 50th percentile, is 65 years for houses that are over 100 meters away, right? They're far away, so over 100 meters away. Whereas houses that are within 100 meters tend to be, the median is 78 years of age. So these both suggest that, older houses do tend to be found closer to the railroad, or at least within 100 meters of the railroad, than younger or newer houses. And this then just illustrates how something as simple as a mean, or slightly more complicated, a median, can be used to compare two groups of, in this case, houses, but you're controlling for whether they're close or whether they're far away from the railroad. And I believe this is the end of this particular section. And then there's one more section after this. I'll start a new video for that, where we move on to talk about associations. And that'll be fun. And we'll use the same data set. See you momentarily.